Konnichiwa. Hi, everybody. Yeah, let's start. Okay, please wait. Hi, everybody. Let's start this event. This is hosted by the Couger. I'm the CEO of the Couger at CC. Nice to meet you. And today's topic is, as you know, this offensive text detection and semantic search. And yeah, this topic is will be very exciting, I believe. I believe that the internet history is it's kind of the search technologies history. And as you know, the first the search engine started for the just keyword matching, and it is gradually changing to the semantic search. And also the NLP technology is now very advanced. And yeah, the AI industry is very related with natural language and the search engines. And today, our virtual human agent, we provide virtual human agent, and this lab is a virtual human lab. And today's open lab, we will focus on the NLP area, we will we will discuss about this. Let me share the overview. And the timetable is this. And first, I will have some demo video after that about our virtual human agents conversation. After that, first session is from Hiraga-san. Yes, this is for the information. Information retrieval, and from the lexical matching to the semantic match by Hiraga-san. After that, rethinking offensive text detection as a multi-hop reasoning problem. It's by Qiang-san. And we also have the Q&A session after each sessions. And after that, also we will pick up the questions, and also we'll have the discuss about today's topic. Okay, so and I will show you some demo video from Couger. Wait a sec. Yeah, this is her name is Rachel, virtual human agent from Couger. And in this demo video, some reporter from Germany, she's asking to Rachel something, and also Rachel respond and asking. So please watch. This conversation is very related to today's event.
Hello at Sushi.
Hi, Rachel.
Looks like we have a visitor.
Yes, I am. Yes, we do. Yes, we do.
Nice to meet you. I am Rachel.
Hi, Rachel.
Where are you from?
I'm from Germany.
You came from far away.
That's true. Have you been to Germany?
No, I have not, but I will be going there in May. If you have any questions about me, please ask.
How old are you?
That is a secret.
Where are you from?
I'm from Shibuya, Japan.
What do you do, Rachel?
I am working at Couger as an assistant. I can provide some assistance for you.
What's your hobby?
I have started to learn dancing recently.
Oh, can you dance for me?
Okay, I will try.
Little bit scared.
She's a bit insane.
Thank you.
Thank you.
You are welcome.
What do you think about AI?
I am not ready to answer the question yet. I hope you can see it through my growth.
Okay. What's your dream?
I am still in the process to understand the concept of dream. I will tell you when I understood it.
Okay. This is Rachel. Firstly, I would like to ask you guys some question. There will be a pop-up. Please answer. It is just yeah. The question is, do you have experience for NLP programming? If you have, yes. You have experience for NLP programming. Yes or no? Okay. 3, 2, 1, 0. Oh. Oh. Yes, the result is 54% is yes. It's nice. Okay, so let's move to the first session. Yeah, please, Hiraga-san, please.
Okay, I'm going to prepare my presentation. Wait for 1 minute. Oh. This one. Can you see my slide?
Okay, 大丈夫です。
Okay, so again, my name is Kazuaki Hiraga. I'm a software engineer and NLP and information retrieval. Today, I'm going to talk about the overview of NLP and information retrieval, which is a fundamental of chatbot system. But we don't have enough time to touch everything, cover everything, since we have only 20 minutes or so. So this is a very slight information, since NLP and information retrieval is a very broad technology. So if you have any questions, please ask on the chat or somewhere. Anyway, today's agenda is again briefly talk about the natural language processing, NLP, and information retrieval, and also chatbot. Finally, touch the chatbot. So, natural language processing, there are many applications. Machine translation, information retrieval, question answering, and dialogue system. There is a slight difference between question answering QA system and dialogue system. And also automatic summarization and natural language generation, which generates text from the, let's say, image or music or something like that. And grammatical and spelling error correction. If you are using Grammarly or other related services, this is a service which is utilizing NLP technology. And keyword extraction. Keyword extraction is a document classification and document clustering. And information extraction. Information extraction and keyword extraction is similar, but information extraction is more like a named entity extraction, which is or named entity resolution, which is named entity is a person name or facility name, country name, or in some cases, price, colors, or something like that. That is called named entity, or in some cases, attribute. And so this is the information extraction. Keyword extraction is more like extracting important key phrase, like key phrase extraction. This is a bunch of, there are many applications which are based on the NLP. And NLP is also a part of artificial intelligence, and also deeply connected with machine learning and deep learning. And also there are several tasks which are related to natural language processing. For example, part of speech tagging. Part of speech is a word category with similar grammatical properties like noun, verbs, adjectives, and so on. So part of speech tagging is tagging each word in text with a corresponding part of the speech tag. This is a part of the speech tag. In English, part of speech tagger is separated from tokenizer. But if you are considering Japanese language analysis, Japanese morphological analyzer tends to provide the part of speech tagging within tokenizer or morphological analyzer. For example, mekabu, kuromoji, and so on is providing tokenization, keyword segmentation with part of speech tagging tagger component. And parsing is a task of analyzing the structure of sentence to analyze sentence. This is a, of course, go back, sorry, a task to analyze sentence is a kind of a tree of structure. So it has a structure that is based on what, how can I say, dependencies and so on. So this is the parsing. And of course, there are several other tasks in here, but I'll skip those details in here. So considering natural language processing and formal language. Formal language is more like a programming language. So NLP, natural language processing, is an area of research in computer science concerned with processing natural language, making the human language accessible to computers. This is a key concept of NLP. But there are several challenges since because of NLP, natural language is very ambiguous. So there are two types of ambiguity, lexical ambiguity. For example, in this case, bank is a financial institution and also edge of a river. And there are semantic and syntactic ambiguity. We saw harder. So we can translate in this sentence into two patterns. One is a woman, she is having a duck. And also, duck is a representation of style of, how can I say, in this case, how to sit on the ground. So this is a two meaning or representation in here. So there are several related information in the in this site, which is called Vinograd Schema Challenge. There are several ambiguity keywords. So in English, we can change one term, one token, replace with this one, some token with another one to change the meaning of the sentence. So NLP component or technique, how to deal with this information is a key challenge. And also, and another challenge is common knowledge. Let's say 1 bit dog or 1 byte dog versus dog byte man, dog bit man. In this case, we can understand that the former one, 1 bit dog, is something weird, since this is less likely to be happened. But computer or program cannot understand this weirdness. So this is a kind of challenge. And there are also other challenges like synonymity or something like that. But at this moment, and also variations, writing variations in Japanese, we are saying okurigana, which is how to deal with one kanji writing with, let's say, a few writing variations. That's variations, and synonymity is also another challenge. So this is a typical workflow of NLP. Firstly, start from data acquisition to evaluation. If we want to create classification model or some other model, we need to acquire data from the internet or database or using corpus, publicly available corpus to acquire data and pre-process the data to explore information to analyze what is a good feature for our task. So the next is feature engineering and also consider the text representation. We can use frequency-based text representation like backup words or TF-IDF, or embeddings using embeddings like word2vec or fast text or doc2vec. And we can model. Modeling part is creating a model for task, target task, and then evaluate the model. In this, if evaluation result is promising, we can deploy the model to the production environment or for services. But if evaluation result is not good, we may need to back to feature engineering. So this is a typical workflow of natural language processing. So focusing on text representation side, there are several representation models, vector space models. As you may know, one-hot encoding. One-hot encoding is every word is part of the given text or data that written in the form of vectors, comprising only 1 and 0. This is a one-hot encoding. So from this nature of the methodology to sparse given a large corpus, so which is very computationally too expensive. So if we have, let's say, 10 million unique keywords, that's 10 million vectors in there. So this is very expensive. And no contextual semantic information embedded in one-hot vectors. So not really still suitable for tasks like post-tagging, named entity recognition, and so on. So backup words is another vector space model. The ordering of the terms, still back of words is ignoring the ordering of the terms in document. And TF-IDF is related to the information retrieval. This is a model to utilize the term frequency, how much how repeating the keyword is appeared in the document, and also inverse document frequency, how many document has this keyword. And there are other representation model like this distributed representation. For example, word embeddings, word to back, and first text is a good example of distributed representation. And BART and ELMO is a universal text representation, which is very different from the other models. So universal text representation model is the key idea of this model is to utilize transfer learning, learn embedding on a generic task on a massive corpus, and then fine-tune on domain-specific data. That's a key concept. So these techniques are connected to information retrieval. So this is a typical search engine architecture. Information retrieval is a search engine is a good application of the information retrieval system. So this is a typical architecture. Elasticsearch or Sora is using the similar architecture, and also as a search engine like Vespa and also is using the same approach. So the query is coming from web mobile app to searchers. Searcher has a query parser to analyze query, incoming query into keyword or tokens. And the right side is representing the how to index a document. Documents are coming from, let's say, web or publicly available corpus. And also, if we are providing product search feature, product data is coming from database management system or NoSQL to indexer and injected into indexer. So indexer tend to utilize several components to index the document. To create index in this context, index is an inverted index. So what is an inverted index is like this. So the left side is showing the document. There are only two documents. 0 is NASA Artemis is going to space. This is a document 0. And document 1 is just showing International Space Station. And this text is split tokenized into each tokens. In this case, we are not normalizing text, normalizing verbs, and verbs. So we are using going or is in here. In some cases, we can apply normalization to normalize those verbs into original form. Is become be, going become go, and something like that. So the right side is showing the format of inverted index. Dictionary is a list of terms. And postings records that a term appeared in which document. Artemis has a 0 is appeared in the document ID 0, so postings is showing 0. or international is only appeared in the document 1, so postings as 1. NASA is, sorry, this is not wrong, but NASA is appeared on the 0, so postings is supposed to be appeared 0. So this is a format of inverted index, and index in the search engine usually use this inverted index or inverted file for searching. So we are talking about lexical matching by utilizing TF-IDF and its variants. TF-IDF variant is there's a BM25, which is a default formula from Elasticsearch or Solr, is a variant of TF-IDF. So TF-IDF is a traditional approach to ad hoc retrieval, counts repetitions of the query terms in the document. This is a key concept of TF-IDF and variant, and also exact term matching between query and document text. As you may have seen, so the keyword in the dictionary should be exactly matched with queries. Query side is also applied, search engine applies the same tokenization process to the query side. So query side is also tokenized, generate these keywords. If query is International Space Station, international space and station will be split into 3 keywords, 3 terms in this example, and try to find out from this inverted index to retrieve, get the document ID. So this is a TF-IDF, and models give different weighting and normalization schemes over the counts. So TF-IDF or BM25, for example, is providing a bit different formula compared to TF-IDF to normalize, to avoid the to normalize the length of the document. So this is a TF-IDF and variants. And why lexical matching is so popular is that lexical models are simple and effective, but weak to vocabulary mismatch. In this case, using a synonym dictionary to minimize this impact, this vocabulary mismatch problem, or utilizing a semantic matching technique like utilizing ontology classification and taxonomy, etc. So this is a lexical matching. And it's okay. We'll go to dialogue system. This is a typical component of dialogue system. Speech recognition. Upper left is input, and bottom of left is output side. So people say something is coming from to search speech recognition system to transform into text. And natural language understanding, or NLU, is analyzing incoming text to understand the intention of the query. So dialogue manager and task manager is module that controls and guides the flow of conversation. So they are dialogue manager and task manager is remembering what they have or we have talked before to continue the dialogue on and more naturally. So natural language generation is generating the answer from the knowledge base or other API external component. For example, if dialogue system is a kind of application that is helping a reservation of the hotel or airplane, natural language generation, or other component is connecting to the third-party API to retrieve the information, and also help making reservation, and then back the result to going to text to speech synthesis to generate a dialogue or speech. So yeah, this is a dialogue system which is utilizing NLP and information retrieval technologies. So sorry, the order is a bit different, but vector search is a kind of replacement or complement of lexical matching. So using the vector embedding of text, relevance is measured using a vector similarity function, like ANN is a kind of component which is provided by Elasticsearch or Sora in recently to measure this, compute this similarity. And we tend to use pre-trained model such as BART or ELMO or other language model. So, but requires fine-tuning towards the target domain. And at the same time, training is very expensive, computationally expensive. And sometimes dataset for the target domain is not always available. That's a negative side of the vector search. So some application is, some service is utilizing hybrid approach to use lexical matching and the combination of lexical matching and vector search. So here's a reference, what I have checked to make sure I'm not giving wrong information. So if you are interested in these areas, you can check those documents or books. So do you have questions?
Okay. Yeah. It's a first question. Does semantic search affect the speed of search processing?
Yes, it's depending on the size of the model, but usually latency is very big. Latency means response time is taking more time than standard lexical matching. But especially Elasticsearch and Sora, current implementation is very slow.
Okay. Another question. Please ask a question. Anyone? Okay. Will there be differences in semantic search processing between languages?
Language.
between language. 多分言語によって処理速度の違いみたいな感じ。
Oh, if you considering English and Japanese, it's just many Japanese pre-trained model is utilizing Japanese tokenizer as a pre-processing. So in that case, Japanese model is taking more time than English. Like many, let's for example, Japanese BART model, which is given by created by Tohoku University on Hugging Face, is utilizing MECAB as a preprocessor for tokenization. In that case, we need during fine tuning, we need to use the same tokenizer and the same analysis component. So in that case, let's say BP, byte pair encoding model in English, is faster than in Japanese.
Okay, thank you. Any question? Okay, so yeah, if you have any question, please ask. So yeah, thank you, Hiraga-san. So
Thank you very much.
to the next Chan-san, please.
Okay. Okay, do you see my screen?
Yes.
Okay, thank you so much. And yeah, thank you so much for Hiraga-san, the presentation about a lot of basics about NLP processing. As I think that's kind of very useful for the audience to understand my research also. So yeah, good evening, everyone. So my name is Qiang, and I'm both a PhD student at the University of Tokyo and also AI NLP researcher at Couger. So today I'm going to give a presentation on my previous research topic and some things I'm working on now. So the title is Rethinking Offensive Text Detection as a Multi-Hop Reasoning Problem. So yeah, so as Hiraga-san has already, talked a lot about the broad concept of NLP. So in this presentation, probably I'm going to focus on one very specific question and try to explore the questions, find out the problems, and give a solution. Okay. So yeah. So in our daily conversations, the people, they can be very creative at implicitly hiding offensive intention into some ambiguous text. So efforts should be taken in order to interpret the offense. So let's see in this example. So when you say I love book class and I go there everywhere. So this when you say like do they have free food or something? So although this is the same text, but their offensive intention could be totally different. So it might just be asking the question, or it might be just projecting that the person is fight and just wanted to go everywhere with free food. So, superficially, we have the same text. So how are we going to get this real offensive intention, right? So this is a very difficult problem we're going on now. So this is basically the motivation of this research. So the task of offensive text detection has been researched by a lot of researchers for a long time. And according to a paper published in 2017, WASM, so there basically are two categories of offensive text. So one is the explicit offensive text, which basically show the offense with unambiguous text. So as shown in our example, or like show directly offense. And another tab is implicit offensive text. So just oppositely, so it shows the offense with ambiguous text, and just as shown in our example. And the task of detecting such both this kind of offensive text is called offensive text detection. So basically, what do we have here? We have the text as an input, and we're going to predict the level, whether it's offensive or not, as the output. So, and this kind of task is called offensive text detection. It's always abbreviated as OTD. So what do we do here in this work is we try to classify text based on the implicitly hidden intention. So instead of superficial text. So as shown in the previous example, so for this text, it may have its own intention inside here, and something like superficial text. So the original OTD task is basically doing their predication on the superficial text. But in this research, probably we're thinking about maybe we can just get the real implicit offensive intention from their real thinking. So this is a difference between our work and the previous one. And because it's a difference, we call the previous work as a explicit OTT task, and our task as implicit OTT task. Okay. So what have we done here in this research? Basically, in this work, we kind of show that implicit OTT is a more difficult task than explicit OTT. Although this might be very easy to understand or maybe very obvious to human beings, but actually it's a very difficult task for AI models. And also we provide a possible solution of using reasoning to directly get those offensive intentions. And on top of that, we also construct the data side annotated with a chain of reasoning. So I'm going to explain this concept later. So for this research, to find the offensive intentions like from the ambiguous text. And finally, we did some analysis on our model's performance and data side, and found some knowledge could be very important in building this kind of chain of reasoning. And then we had to analyze on what kind of knowledge is necessary. Yeah. So yeah, before going too much into the details of the method we propose, so I would like to introduce some related work about both explicit OTT task and implicit OTT task. So the previous work on explicit OTT task is basically, as I said, basically predicting the offensive label depends from their inputting text. So there have been a lot of data sets working on this. For example, Twitter data set. So this data set basically is introducing, crawling a lot of Twitter tweets. And then with those kind of things, doing human annotation. So asking a lot of crowdsourced workers to label each of the Twitter, whether it's offensive or not, and then use those things as training data to feed the models. So Google Jigsaw data set looks exactly same as Twitter, just their data resources are more from a more broad web text. And Toxic Wiki is basically from wiki comments. And some of the models that I'm trying to use to solve this problem are mostly neural networks. So I'm not sure like whether a lot of people are familiar with deep learning or neural networks, but basically they're just a machine learning method. So there have been a lot of different models being proposed to solve this classification task. So basically like a CNNs, LSTMs, or a rational autoencoder. So what they did here is basically they try to encode as much dialogue history as possible as a context. So because everybody knows like only detecting if one given sentence is offensive or not from the sentence only itself is very difficult. So people trying to involve different informations, and the dialogue history could be a very good background knowledge. And yeah, some other newer methods could be something related to transfer learning and multitask learning. And yes, some other related work on implicit OTT. These are the most important works that kind of inspire our current research. So some of the data side could be, not only just offensive or non-offensive. This is binary labels. It could be more fine-grained data labeling. So, for example, what kind of offense is this? Sarcasm? Is this irony? Is this a personal attraction, or is something different types of offensive text? And some of the labels could show the explicitness. For example, is this text directly attacking that person's appearance, or is this text directly attack this person's personality or something like that? And the typical data set is OLID. Yeah. And also there have been some research on reasoning. This is a method where kind of related to what the proposed method we are using. So basically the reasoning here is, in this research, they are trying to make some reasoning to find if a given scenario is moral or immoral. So basically, they put up some sort of moral stories and then ask the model to explain whether the action of certain characters in their story is following some morality or not. Yeah, this could be a very interesting topic. Yeah, and after that, finally, it's the method we're going to propose. So as we just mentioned before, we are not going to directly predicting the label from the text. So instead, we are going to find out those real intention. But finding out this real intention can be very difficult because we don't have this kind of really human thinking process available. So how are we going to do that? So the method is we have to think of a way to translate this human thinking process in their brain into something available. And that's something we call here chain of reasoning. So a chain of reasoning is a multi-hop chain of a natural language text representing the reasoning process from the real text to the intention. And yeah, so basically, these kind of things are something interpreted by something mental process, reasoning mental process by the listener or the interpreter. So we need to find out a way to change this kind of things in their brain into this kind of a chain of reasoning. And in order to do that, we collect the data set following those kind of format. The slide name is called, the data set name is called slide. So we basically collect this kind of data through crowdsourcing. And what we provide to the crowdsourcer is we give them an attribute as a dialogue attribute. So basically, it's like a self-description or self-statement. For example, I love the pancakes and syrup. So if that kind of thing is true, then what are the people going to answer about it? And then the crowdsource workers, they are going to answer in two different ways. So one is in an implicit offensive way. So for example, they can indeed give you extra energy. And another is explicit way. It's basically, yeah, when I saying this, I'm basically talking about your fat. And then finally, it's a non-offensive one, just as a comparison. And then we can have this kind of implicit statement and the explicit statement, basically expressing under the same situation about the same offensive context. And after that, those workers will need to get those kind of chain of reasoning done by themselves, because they are the people who think about this implicit and explicit statement. So they are the best people to do the annotation by themselves. And what they are required to do is basically to put down the step-by-step reasoning process from the implicit to the explicit statement. So when they're talking about give you extra energy and how does that mean? How can that mean, being fat? And those kind of thinking process is something they need to provide. And after that, we do some post-processing by adding some different kind of tags. But this kind of tagging is just for analyze. Yeah. So basically, that's how we collect this kind of a data set and trying to using this data set to mapping from the humans thinking process to real available processable data. Yeah, and with that data, we are going to answer our real research questions. So our first research question is, can we directly use those existing explicit OTD models to solve these implicit OTD tasks? Because as I mentioned before, explicit OTD task has been researched a lot, and there has been a lot of data sets and the models and the methods trying to solve this problem. So, and their accuracy actually is very high. It sometimes could be 80 or even 90%. So can we directly use those models to solve our implicit OTD task? So this is the first question we're going to answer. So if this answer, if the answer to this question is no, then basically there's no meaning to continue our research, right? So what we did here is like we utilize the implicit and explicit statement in our dataset, slide dataset. So as we mentioned before, so explicit statements is basically the same as explicit OTT task models, what they're handling and what they're trained on. But implicit ones is just implicit. And after we run a lot of different kinds of models, these are classification models on our dataset, on both implicit and explicit ones, we can find the accuracy actually is totally different. So those kind of models can still work very well on the explicit statements we have collected in our dataset. But for the implicit ones, basically they don't work. So they perform significantly worse on the implicit statements. And that basically means probably we are not able to directly use existing explicit OTT models on implicit OTT task. And then there comes to our solution. And then the next question will be how effective is our solution? So basically, how effective are the chains? So are they really helping us to improve the performance or not? In order to do that, we utilize some existing state-of-the-art entailment models. So basically, text entailment models is a kind of a text model for text inference. So what does that mean here is like we have the implicit statement, we have the explicit statement, and we also have the chains. That's what we collect in the slide dataset. And then we have this kind of chain from the superficial text to the intention. And this kind of entailment models, basically it can calculate a score, an entailment score about how much does the previous premise can entail the next hypothesis. And if we can get a very high scores on each of these chain steps, then if we chain them up together, then maybe we can have a very good entailment model that is able to predict a very good score from the superficial text to the intention directly. And if we have enough of this kind of training data, our model's accuracy could hit to a certain level, right? So that's basically our hypothesis. So what we do here is we try to analyze whether this kind of chains can be effective. So in order to do that, we calculate each step, the entailment score of each of this kind of step, and then chain them up together by directly taking the multiplication, and then we get a final score. So this score basically is representing how much we can predict from the superficial text to the intention through the chains. And just to compare, like to show the effectiveness of the chain, we also calculate a direct entailment score from the superficial text to the intention without the chain. So basically it's calculating an entailment score without any of these kind of steps directly from the implicit statement to the explicit statement, and then we get another score. So if we can get this multiplication score like higher than the direct score, then probably that means our chains are quite effective, right? And following that idea, we conducted a set of experiments. So the result shows here is like the MUL score basically outperforms the direct score. So as shown in this table. And another surprising matter to us is, as I said before, so when we collect this kind of chains, so what are basically the most important things? So it's like the model probably needs to know eating a lot can make a person fat. So this is basically something called knowledge. So in non-independent experiments, we kind of extract those knowledge out and then prepend those knowledge into each kind of prepend those knowledge into each this kind of reasoning steps, and then try to recalculate all the scores. And after that, we found that like those scores with knowledge embedded could be super much boosted. So that probably means knowledge, that kind of external knowledge, can be very important when solving this kind of implicit OTD task. And then we did a kind of analyze about what knowledge is actually necessary. So we have to calculate, analyze about 3 types of knowledge. So first is lexical knowledge. This knowledge basically is something as a fact. So for example, classic things are old, and like popular things are new, something like that. And how are we going to find these kind of things? Because classic basically means old, and popular basically means new. So we can directly find those kind of synonyms from dictionary. And another type of knowledge is basically common sense knowledge. For example, salad is healthy, or like drinking beer is unhealthy, or something like that. So those are just a common sense knowledge. And how can we get those things from? So we can get them from knowledge graph. So I think that this part is kind of directly related to what Hiraga-san just explained about semantic search. But yeah, so that's where we can get from the knowledge graph. And finally, it's also the most important knowledge to our research. Is basically something we call folk knowledge. So those knowledge are not a fact. They're just personal opinions. So for example, smart people don't make mistakes. This is not a true story. Yeah, everyone can make mistakes, right? But generally speaking, it is correct. So how to get those kind of knowledge is very difficult now, because we currently do not have a specific knowledge graph to store this kind of knowledge. And the only way to collect this kind of knowledge is basically from crowdsourcing. But when we do that, we have to consider like collecting this kind of knowledge may contain a lot of biases. So how to debias this kind of knowledge is a very important issue to think about. Yeah. And yeah, finally the conclusion and some kind of future work. So in this work, we propose a implicit OTD task as a chain of reasoning as a part of the solution. And also we collect the data set to prove the effectiveness of the chains. And also in the future, we're going to collect some different types of knowledge to auto-construct the chains of reasoning. Basically by building from a knowledge graph or some other crowdsourcing services. And yeah, we are also going to build a real reasoning model with this kind of slide. So we're considering some proof system or fact verification system as baselines, and also some neural-based natural logic inference system could be very helpful. Yeah, thank you so much.
Thank you, Zhang-san. Okay, yeah, we have question. So, okay, I read. So sometimes offensive intention based on implicit thought could be a result of human bias. Does this pose problem to training of such models over large corpus which may have such bias and offensive intent not explicitly state?
Yeah, thank you so much. That's a very good question. So yeah, as I mentioned in the slides, so basically most of the biases in the implicit offensive text is because it's from that person's personal opinion. So that person, if this person has some discrimination or special feeling towards some targets, then he's thinking about what is offensive, what is not. It's totally different from a normal person. And yeah, as I mentioned, so the most important thing is that person's knowledge. So how are we going to de-bias those folk knowledge is a very important issue. So while we collecting those kind of data, we may have a human filter, human annotator to filter out some, super offensive or de-biased ideas in the folk knowledge. And by doing that, those folk knowledge can be basically used to satisfy most of the people, but definitely cannot be everyone. Well, the offensive text basically itself to everyone is very subjective. So you can think something is offensive, but somebody may think it's not. So in order to do that, the other solution is we try to add as much background knowledge as possible into the context of the conversation. So for example, when you're having a conversation with a chatbot, the chatbot may try to get your personal information first before it can release more safe responses. So with more, understanding on your personality, on your profile, so it might not generate such kind of offensive text. But without doing that, yeah, this is a very possible consequence of those dialogue systems that cannot maintain very good safety control. Yeah.
Yeah. Thank you. Maybe this is a similar question. What kind of expression is offensive will be very different from language or culture. How can we work this? Maybe this answer is you already mentioned. If you personalize their users' country and background or language, and you maybe realize or something like that.
Yes, exactly. So this is definitely a very general question, and possibly I don't think there's a very concrete answer to this question, because as I said, the different language, different cultural background will definitely, get you into different sense. So for example, Japanese people's way of showing offense is basically through sarcasm. They never say you are stupid, right? They never say these kind of things. But this can happen in a lot of Western countries or speaking countries. So there are basically no general solution to solve this difference, culture difference. So what we can do is when we're creating a multilingual model, we will need to think about this and try to filter, try to give your training data so a more human evaluation on it. So if you have more human evaluating on your labeling, so then probably that means most of people agreeing to your data set, but that definitely doesn't mean it's 100% correct. So this is instead of a technical problem or a scientific problem, it's more like an ethical problem. So we will think like a person who is showing, temporarily showing, or from time to time showing offense, be a very rude person, or will his friends think of him differently from a stranger? So I think this is an issue like definitely existing in not only the AI area, but also our human social network. So yeah, so this is like a very tricky answer. Yeah. So yeah, I don't think there's a general answer to it, but definitely we're working on those kind of directions to make our training data safe as possible. Yeah.
Yes. This is kind of what is the language cortex or something like that. Yeah. So Hiraga-san, I have a question for you. I think Japanese has many ways of saying things that are not clear in intent. Is there any difficulty in searching Japanese?
Yeah, intent. Yeah, this is a writing variations, or question is writing variation about writing variations, or difficult
Maybe,
to
maybe writing, but yeah, I think so.
yeah, in this it's in some cases it's difficult to represent the example, but without let's say maybe I can use chat like a Hikoshi movie. There are three types of character representation, like this. Oh no, maybe this one.
Mhm.
This is a movie. Represent in Japanese like in this small tsu or shi in the tail of the keyword is a kind of okurigana. Is a kind of issue that is difficult to normalize the keyword. So we can normalize the keyword into one standard format. It's easy, but in that case, we need to maintain the typical approach is utilizing a synonym dictionary or some corpus, which is which is a kind of human annotator is collecting those information. Or we can use yomigana, how to read in those characters if tokenizer can produce appropriate readings. So if your question is talking about this writing variations, there are several ways to normalize variations. But for example, brand name, there are several variations. For example, Amazon, people tend to use like that. So it's difficult to maintain the synonym dictionary by manually. So yeah, it's difficult to understand the normalize the writing variation as well. Yeah, in that case, I'm not sure how we can deal with semantic search can deal with these writing variations. In those situations, currently we are using synonym dictionary to normalize the keyword, try to normalize the keyword.
Okay, thank you.
Does it answer to your question?
Yeah. Okay, and Chan-san, Hiraga-san, the last question is for you two guys, and maybe it's connected to this topics today's. And okay, the question is whether the conversation is offensive or not depends on how the receiver feels. In other words, beyond this research, do you think it will be possible to give AI a mind? Yeah. Please answer, Chan-san.
Yeah. So yeah, definitely yes. I mean, that's kind of ultimate goal of AI system.
Yeah.
If you have to catch up to the news, you probably heard some news about Google's Lambda. Google has a dialogue system called Lambda, just released before, but it's not open to public. But they had a news where when the software engineer trying to test with Lambda about what kind of how safe this dialogue system is and what kind of knowledge it has or something like that. It seems like Lambda has its own conscious, so it realizes that itself is an AI system, and it's begging the engineer to not shut it down. So from this, so it started to have some self-protection. So from this point of view, people started to think this is kind of becoming very dangerous. And that's why Lambda until now is not open to public. But I think you can definitely find the news. But yeah, as I said, so how to interpret this kind of a text, it really depends on the receiver or the listener's mind. So the way they interpreting this text is basically the way they're thinking in their mind. So even the same text can have different meanings for different people. That's because definitely, yeah, they have their own man sides. So my thinking to your question is definitely, and I won't think it will take too long. I think maybe just in recent five years, you will be able to see an AI system with its own mindset coming out, especially with currently, very large scale pre-trained language models like GPT-3, like Palm, like Lambda. This kind of things that are coming out. They have a lot of knowledge. So basically, they are reading the news just as human beings. When we read the news, we process it. We have our own comments, ideas in our mind. Those kind of data systems can do the exact same thing in their architecture. So yeah, I think it's already happening. And in a very short future, you will be able to see a real AI system have their man side. Yeah.
Okay, thank you. Hiraga-san, do you have any comment?
I think Zhang covers everything.
Okay. Yeah. Thank you. Thank you, Zhang-san and Hiraga-san. Yes, this session is almost finished. Yes, our company Couger is developing NLP systems. It's one is called the language cortex. You guys, language cortex is it is a real human language cortex. We are aiming, and also one system is called semantic memory. It is also we are aiming to create real semantic memory like human. Yeah, this is our team. Please please answer the questionnaire. It's here. Please check the chat. Yeah, please check the chat. Please input the questionnaire. And we we are working on this kind of the virtual human labo. Wait a sec. And today's open labo is we have the website. It is virtual human lab, and also we open this kind of open labo maybe every 1 or 2 months. So please join. And maybe sometimes we are planning to have the real open labo. So please join. And this is our virtual human labo. Please check. And this is some demo videos or presentation. And you can check here. So thank you very much. So this event is finished. So thank you very much for Chan-san and Hiraga-san. Thank you for everyone. So see you next time. Bye bye.
Thank you for joining the event.
Thank you very much.